approximate area under the curve from A to B. So if you add these all up, so then how do you make your estimate more accurate? You take more and more divisions. You make more and more divisions. This is nice and comforting because it's in 2 dimensions. And you're adding up rectangles. Generally speaking, not generally speaking, but do you need to have a uniform width for this to work? Like, do you have to have the same width between each one? Do you? You actually don't. If you're increasing the number of slices as you go closer and closer to infinity, essentially what's going to happen is they're going to pack all together and they get really, really small. So it doesn't actually matter. The limit is still going to stay the same. But mathematically speaking, to make these computations work nicely so that you don't have to do really weird things, we generally take the slices that all have the same width. Generally speaking, what's each width called? Dx, exactly. Okay. So let's extend this to different places. So what do I see here? I see a set of points. This set of points exists in R3. What is R3? 3 dimensions, 3 space. So S represents all of the points in 3 space such that, where does Z exist? Between the floor, the xy plane, and the height. This blue thing is f of xy, and f of x and xy. Where does xy have to exist? Yeah, this not no. Well, in this case, it's a bit kind of poor notation. They don't mean all real numbers with that are. What do they mean?
It's an element of some.
It's the actual what?
Square.
It's the. You could say that's the domain of the function. The domain of f of xy. It's, again, mathematicians sometimes use pretty poor notation. It's not all real numbers. So what you're trying to do is, instead of finding the area under a curve, you're finding the area under a. What's that? What would you call that blue thing? Instead of an area under a curve, area under a surface. Exactly. Area under a surface. We're starting with functions of the form z equals f of xy. This is as simple as we can make it. So what we've done before, just to put this in perspective, is you have integrated across one slice of this. You've integrated things like you've had the function right there, and you've figured out like what's the area of this slice right here. You've done things like that over and over and over again. Extending into 3 dimensions, how many of those slices are you going to integrate? Or how many of those slices are you going to find the areas of? An infinite number. So the first thing you do is you're slicing this one slice up into lots and lots of rectangles. And then you're just adding an infinitesimal piece into the 3rd dimension and then scanning across this shape. If I took a shape and I sliced it up, you ever seen those bodies down in Boston? Well, they're in Boston for a little while. The bodies that have been sliced up. You ever heard of this? They take a human cadaver, they preserve it in the proper way, and then they slice it, literally essentially freeze it in place, and they slice it so that you have unbelievable cross sections looking at it. What you're doing, it's brutal. What you're doing is you're effectively finding the area of each slice and adding. You're effectively finding the volume of each slice, and each slice is really, really thin. And then you're adding together all those volumes to get an estimate of the volume of the 3-dimensional shape. But you're making each slice infinitely thin, so you end up getting closer and closer to the actual volume of the 3-dimensional shape you were looking at. And we're going to look at a very narrow slice. So instead of having an area under a curve like this, so here's our curve, and we're going from A to B, and here's our x-axis right here. So there's the x-axis. Each shape is a rectangle in this case, where you add up lots and lots of rectangles. And that goes a little too far there. What's the width of each of these rectangles? Delta x. And the height right there would just be f of some x value. Let's say x sub, I don't know, star right there. Some x value. But you multiply height times the base in order to get the area of a rectangle. So we're not adding together rectangles anymore. What are we adding together? Rectangular prisms, exactly. So now we have a shape poorly drawn that looks like this. One of the bases is going to be delta x. The other base is going to be delta y. And what's the height going to be? F of x, y, some star right here. Some index. You need 3 things. So what you're going to see here is this expression right here. What does that delta A represent notationally? The base area. That represents the base area right here. So what's another way to write the base area? Delta x times delta y. Literally speaking, delta A is going to be delta x times delta y. That's it. And what does this represent right here? The height. The height for that box, for that sample point, evaluated from that sample point inside that box. That's it. That's what that notation means. For decoding purposes, keep in mind that the x values, you have xi, j, and yi, j. First, the first one that's indexed is j, and then the second one that's indexed is x.
Can you briefly go over that notation?
So the notation, I'm sorry, let me go back. I'm sorry. I'll go back to that picture. Let me go back to the picture. 1, 1, 1, 1, right? Great. And what's the height right here? We said the height right there was 4. The height right here was, oh, excuse me. We don't want that height. We want that height, correct? So these are our heights. You want to find out the heights of each of those. So this point right here is going to be, the base is 1, 2 right there. This base right there was 2, 2. This base right here was 2, 1. And the base in the center, 1, 1. So you plug those in. The base in the center is going to be, how high is this? What's the height of this point right here? 13, right? Agreed? 1 minus 9. So what's the height right there? What is it? Isn't it 7? Isn't it 7? And then what's the height right there? Minus 4 minus 2 is 10, right? How is it 7? Because it's 1, 2. It's 1 on the x and 2 on the y. 1, 2, right? So what's the base of each of these is 1, and we just found the height of each of them. What are they? 13 plus 7 plus 4 plus 10. So our estimate for this thing, which we know is an underestimate, is 34. So how do we make this more accurate? What do? Make them smaller. You keep breaking them up, you keep breaking them up. So if you keep on breaking these up, the math becomes kind of annoying, but it's not bad.